We're going to do another 2 days of optimization problems just because there's a lot of different things that you can see with these problems, not because they really get too much harder, just to get more examples. So this first one here, or we only have one example today, but this example that we have here is find two numbers whose difference is 100 and whose product is a minimum. We don't really have anything to draw here because we're just looking for two numbers. So let's let x and y be our two numbers. So that's what we're looking for. And so the first piece is telling us that the difference is 100. So x minus y is 100. It wouldn't have mattered if you did y minus x. The roles of x and y are interchangeable here because we're just looking for two numbers, not looking for them in any particular order. So this is an equation that is equal to something. So this is our constraint. And what is the thing that we're trying to maximize or minimize? Whoopsie. That's their product. So we want that product to be a minimum. So we want to minimize. That is not how you spell minimize. Sorry, you guys can correct the spelling there. The product is x times y. Okay. Notice in this particular problem, we are not given bounds. And so you remember last time we came up with a closed interval that we were working on. In this case, we do not actually have a closed interval. They're not telling us that these numbers have to be positive, so 0 is not a lower bound. Also, these numbers could be as big as we want them to be. There's no set thing that these numbers have to be smaller than 100, because you could find two numbers bigger than 100 whose difference is 100, like 300 minus 200. So we have no bounds in this case, which you might think, uh-oh, that's a concern. We're going to figure out how to deal with that in this particular problem. But let's just keep working and then we'll worry about that in a minute. Okay. So we're going to do what we did last time. We're going to solve the constraint equation for one of the variables. I like to add, so let's do x is 100 plus y, and then we're going to plug that into the function that we're trying to minimize to get it in terms of a single variable. So that tells us that p is x, we're going to replace with 100 plus y times y. If we multiply that out, that gives us 100y plus y squared. We're trying to minimize something, so we need a derivative and critical numbers. So the derivative is 100 plus 2y. If we set that equal, we're going to get y or equal to 0. We get y equals negative 50. Okay. So now we have to try and decide whether this is a minimum for this function or not. Last time, this is where we would have used our bounds, but we don't have any bounds. So you might remember from last semester, we did number lines to try and determine whether things were maxes and mins, and let's do that here. So we'll do a number line for the derivative. We'll put negative 50 on here. We're looking at, this was our derivative. So remember from last semester, I pick a number on either side of negative 50. So something a little bit smaller than negative 50, like negative 51. If I plug that into here, 100 plus 2 times negative 51, that will be negative. If I pick a number a little bit bigger than negative 50, like negative 49, again, if I plug that into the derivative, that will give me a positive value. Okay. Last semester, based on what we did last semester, this tells us that we have a local min at negative 50. But with all of these optimization problems, we want to have an absolute maximum or an absolute minimum. We're looking for the very biggest or the very smallest. So just having a local min is not good enough. But this is where the first derivative test for absolute maxes and min comes in. So there's a lot going on here, but essentially what this tells us is if we only have one critical point, and if at that one critical point, we have a positive on one side and a negative on the other side for the sign chart of f prime, then C is an absolute max, not just a local max, it's an absolute max. And that's because we only have one critical point, is that the function is going to look something like this. And then the same is true with a minimum. If we have a sign chart that looks like we got up here and we only have a single critical number, then that local minimum will actually be an absolute minimum. So in this particular case, this is an absolute min as well. So our coordinates or our numbers would be y is negative 50, and then we have to figure out what x is going to be. We can plug negative 50 into here. So x will be 100 minus 50, which is positive 50. So our two numbers whose difference is 100 and whose product is a minimum are 50 and negative 50. So when you can find a closed interval, then you deal with the problems like we did last time, where you plug the numbers in to the original function and see what gives you the biggest and smallest value. If we don't have a closed interval to work with and we only have a single critical number, then doing a sign chart and showing that we have a min or a max there will show that you also have an absolute max or min.